Hello, good morning, everyone. Today I'm going to start the design of flexible road pavement. So in this chapter, we will talk about the design of the pavement um, when, by the empirical approach or by the mechanistic approach. Okay, so but we did this one will be just restricted to the flexible pavement, so we are not going to do anything on the rigid pavement. So the pavement structure. Okay, so I think we have studied the pavement structure before. They got many layers. So a flexible pavement is structured to transmit loads imposed at its surface to the formation level or subgrade. So all the loading will be transferred down. We transmit down from the top with the varying cost, go through the best cost and sub best and to the subgrade. Okay, so in the flexible pavement, the area over which the load is supported increase with depth. Okay, so that the stress in the pavement decrease with the distance below the pavement surface. That means that at the top, the loading is very concentrated on a small area, so the stress is very high. But it when it goes down, the load goes down, it's spread out, so the area become bigger, but the loading, sort of the pressure, the stress will become less as it goes down. And so um, the stress will be the least, at the bottom, the subgrade. We so that's the reason, that's the reason that we can design um, weaker layers at the bottom with for the best cost, the wearing cost has to be highest and followed by the best cost and then sub best, and then at subgrade level we can have a much lower CBR. This behavior has enabled flexible pavement constructed predominantly of unbound granular materials to utilize a range of materials of varying quality. So we have different type of flexible pavement. Some of them, they have the bound layers. Some have unbound layers. So um, we for the unbound layers, for this one, they are just they are not bind together by anything, or by cement or by bitumen or anything. They are just um, loose loose uh, uh, loose aggregates. There are different types like sand and gravel, limestone, crushed rock. So they are loose. They're just been spread on the road and then being compacted by by this roller. The higher quality materials are placed at the top of the pavement where the stress are higher, while lesser quality materials can be utilized at the lower levels of the pavement. Like what I said just previously, just now, the at the top, higher stress, so they use the higher quality materials, and at the bottom, the lower stress, so they use the lower quality materials. The basic nomenclature for the underlying for the layering within the flexible pavement is as below here. So normally we have a surfacing or the wearing cost. Okay, so we have best, or we sometimes call it best cost, sub best. The When the sub best is quite thick, it's more than 200 or 300 thick. It could be subdivided um, into like upper sub best and lower sub best. Okay, so here it mentions that lower sub best might be stabilized soil as well. Yeah, there are some instances, we use the sub best, we stabilize the soil with like cement, or cement. So the subgrade is natural soil. In addition to the traditional or conventional flexible pavement, other form of flexible pavement which make greater use of the structural properties of asphalt have been developed more recently in response to the increasing demand placed on the pavement performance with increasing traffic intensity and loading. So we could you know, the with the thickness design, you know, when there's a more traffic, probably we could increase the layers, but that one is would probably sometimes probably is not efficient. You know, we don't want to get pavement like 1 meter thick. You know, so instead of going thicker, we can strengthen the layers. So so we could, like in this case, we got called the deep strand and full strand pavement. Deep strand is where both the wearing course and base course are comprised of asphalt. Normally, the for the unbound pavement, the unbound pavement material, the base course is just loose aggregates. So in this case, you know, for the deep strand, so the base course, apart from the, you know, the wearing course, also is been mixed with the bitumen, sort of become a sort of asphalt, but it may not be as strong as the wearing course. For full depth, all the pavement layers above the subgrade are comprised of asphalt. So the bottom also then put some bitumen, so they mix with bitumen, so they become bound and strengthened. So you can see that the different scenario. So the first one, the top one is the unbound granular base. You know, this one is a thin, is a wearing course. All this is unbound granular pavement with thin asphalt surfacing. So this one is just thin asphalt surfacing. Thin means that maybe about 25 mm up to, I think, up to 40 mm. So there's a thin asphalt surfacing, and then you with the unbound layers, base and subbase. Unbound granular pavement with thick asphalt surfacing. So this one, the asphalt will be thicker. We're talking about maybe 150, 175 thick, 200 mm thick. So, but we still use the unbound base and unbound subbase. Okay, so so the bottom, the deep strand and the full depth. So this one, the deep strand, just now as we mentioned, the best cost will be best cost. Okay, it will be mixed. So the, you know, the intermediate cost, asphalt best cost. Okay. So here is this one, the, you know, they could have the bottom one as well. They could do the bottom one. They put some like cementitious material, like cemented granular. So this one is cemented. But so by definitions, you know, the best cost, if it's deep strand, is that is sort of you know, have to be the best cost need to be like asphalt, and it's called the deep strand. Whereas in this case, I think the bottom part, it's mentioned the best cost. So there's, I think there's a different terminology. We could like top part here, we could do it as the subbase, soil subbase. But here, you know, okay, anywhere they are above the best cost and or subbase, they are all of them that are just aggregate, and usually the subbase has a bigger aggregate size. Okay, so in this case, I think that this one I got it from the Austroads, so they term it as unbound or cemented granular best cost. So that means that this one, it could be unbound, or it could be bound, or cemented means bound, cemented granular viscose. On the other hand, for the full depth asphalt, all of them will be there. Got asphalt viscose, you know. So all the layers below, they could be like different. So they got they just put it as asphalt viscose. Okay, so that means all the layers above the subgrade, when it's bound with asphalt, so they are bound with bitumen rather, they are termed as a full depth. Okay, but only part of it is been bound with bitumen, so and then with other part is unbound or with other material like cemented, they are termed as a deep strand. Okay, the pavement behavior. We know that the pavement is the materials that comprise the pavement, you know, is beside aggregates. We also have the bottom part is a subgrade, so there's a natural soil. That one is based on compaction, and then the top part is the wearing cost. And besides the aggregate, it also has the bitumen. Okay, so the bitumen, it has the property of I think it's called it is quite elastic, you know, because and then it's called it is dependent on temperature. When the bitumen becomes softened when the temperature is higher, and become hardened when the temperature is lower. So under repeated application of stress and strain, most pavement materials will eventually exhibit some form of distress. So in the course of time, 2 years, 3 years, 5 years, 10 years, there will be some form of distress in the in the form of maybe deformations or cracks, and other thing like edge break or potholes. There will be a lot of usually pothole will happens quite more often. The form of distress that depends on the natural materials as outlined below. So the granular materials may suffer some permanent vertical strain, example rutting, or shear failure under vertical wheel loads. The bound material usually exhibit tensile cracking due to flexure and sometimes permanent vertical strain, also rutting under vertical wheel loads, and permanent shear strain, shoving under horizontal force. For the granular material, for example, you know, the subgrade is a granular material. The pavement which is unbound, they also considered as granular material. And for the bound materials will be, you know, anything that is added with bitumen or cement or cementitious. They are the bound materials. So the bound material will exhibit, besides the vertical strain, also some cracking, but the granular material will only exhibit vertical strain rutting. So this means that, you know, rutting, the wheel track rutting is mostly confined to the wheel track, which is sinking. You know, the wheel track is deep. There is some depression along the wheel track. You know, there's some is sort of been big. It's been lower. The ground level below the wheel under the wheel track is much lower than the other area. So just it mainly confined to the wheel track. For the cracking, so this is a crocodile crack. The cracking initially is it could be horizontal cracks or vertical cracks, not vertical, horizontal cracks. It could be or rather is transverse crack, or the longitudinal crack, diagonal cracks. And when all these cracks, when they are joined together, they become the crocodile cracks. Okay, so When other place there's no crocodile, they call it, like North America, they call it alligator cracking. Okay. While there are several different forms of distress which can manifest themselves in flexible pavement, only two are directly addressed in the design process. So we in the design process we sort of simplify the distress. Okay, so we just we try to make some simplification about the distress. Okay, so we cannot cover like all the things that actually happen, but we sort of simplify into deformations and fatigue cracking only. Okay, so that means that just the deformations, just the rutting, the sinking down, under the wheel track, and also the cracking. Deformations or loss of shape is measured at the pavement surface and is assumed, and hence rutting or densification in individual pavement layer is assumed to be zero. Okay, so that means that we assume that the purpose of design to occur entirely at the subgrade. So the deformations, even though we see that just now the wearing cost it could sink down, but sort of we assume that for the purpose of design, the rutting or densification in individual pavement layers is assumed to be zero. So the top one we don't consider as deformations, but only for the subgrade, occur entirely at the subgrade. So even we know that the layers can sink down, but sort of mainly because of the subgrade. The subgrade, so it costs the subgrade causes the deformation of subgrade. It will results in the top part being sort of also deformed. So in this case, we only consider the deformations at the subgrade. Okay. Fatigue cracking occurs only in materials which transmit load in bending and which are subjected to cyclic tensile stress, as occur in asphalt and other bound layers under the action of traffic. So the fatigue cracking, these are cracking. Normally, for layers to exhibit the cracking, is if you go like this, when the top part usually is compression. The bottom part when it's shortened, it's called compression. When it's lengthened, it's tension, and the cracks we call it the tensile cracks. Okay, so the any layers for the this one, the pavement, for example here the wearing cost, the tensile cracking will happen at the bottom of the wearing cost. Okay, so and but of course when the bottom crack, the cracks will transmit upwards, so the whole thing become cracked. Also, if you have some bound layers, you got the asphalt, the deep strand or full depth, or even the cemented sub base or base course, it could as long as they are bound, they can exhibit the cracking, and the cracking usually happen at the bottom. Okay, because the top usually is when the loadings come down, the top part usually under compression, the bottom is tension, so the cracking usually happen at the tension part. For conventional flexible pavement surface with a thin layer of asphalt or spread seal, the only mode of structural failure is deformation, because of unbound granular materials transmit load predominantly in shear, not bending, so that significant tensile stress do not develop. So when the top part, the asphalt is very thin, or use a spray seal. Usually we just assume that the pavement failure is due to the deformations, mostly due to deformation, because the asphalt, when it's very thin, this is considered as non-structural. So there's no structural. It doesn't add any strength to the pavement when it's very thin. Just like the spray seal is so thin. It's mainly used for other things, for the smoothness, for the sort of water resistant, and to sort of to get rid of the dust and so on. But it doesn't really add much strength to it. So even the very thin, like 25 mm asphalt on top, it doesn't really add any strength to the pavement. In other forms of flexible pavement, like you have a thick wearing course, or you have some bond layers in the pavement. So both modes of failure have to be considered. So we have to consider both the cracking and as well as the deformations, because of deformations, whatever type of pavement, whether bound or unbound, they all the subgrade usually exhibit some sinking or this one, the deformations. So we need to that always whether we still have to consider the deformation for subgrade for all types of pavement. Design philosophy. The two philosophies which are applied to the design of flexible pavement are commonly referred to as the empirical procedure and the rational or mechanistic procedure. There are two types. So empirical and rational or mechanistic procedure. So for the empirical procedure, we're going to look at this one is based on the a chart. Okay, this is a chart from Austroads guide, figure 8.4, design chart for granular pavement with thin bituminous surfacing. Okay, so in this chart, the aim is to find the thickness of material. So to do that, we need to know what is the design traffic. So in this case, it's ESA. So we will cover it later on. ESA stands for equivalent standard axle. Okay, so DESA is design equivalent standard axle. So we also need to look at the CBR. Okay, the CBR. So all this line are the line, slope line. So this one, this line is CBR 2, 3, 4, 5, 6, 7, 10, 12, 14, so 15, 20, and then this line is 30. So we don't whatever this CBR we consider, we only go up as far as 30. Above that, we just because we need to provide the minimum thickness. So when you, let's say you got amount of traffic, and then certain CBR, let's say 10, you draw a line upwards, and then you meet the 10 line, and then you have to project horizontally to the left, and then you can find the thickness of the material. The empirical procedure, as the word suggests, is based on the observations of performance of existing pavement in service, supported by experimental work on specially constructed pavement subject to predetermined loading. So this one's by empirical. You do things empirically. It means that you do some experiment, do some labs, observations. You get some result from the experiment data. So it's an observation of the performance of existing pavement. So they probably they have certain rods. The rodding authorities do some observations on that rod to come up with certain the strength and then see how well it perform against all the traffic, and therefore they have the certain thickness of the asphalt and how it performs. Or sometimes they have this they got a test strip, they got the test pavement, they construct certain pavement, maybe different thickness, they got a different, so they can compare the performance of the various strip of the pavement. So that's what we call the empirical procedure. So all these are testing, from observation, and after many years they can come up with a chart. If necessary, they could revise the chart as well. These observations resulted in a design method known as CBR method, based on the strength of the subgrade as characterized by its Californian bearing ratio (CBR) and the traffic loading, categorized as light, medium, and heavy on the basis of the vehicle wheel load. So just now we talked about this. This is the we base mainly on this chart to find the thickness of the material. They show you the thickness of the all the different layers, the sub base, the base course. Okay, so only all these two layers. Okay, and the wearing cost, we don't do that anything. We just assume it's we only use for the thin bituminous surfacing. So we don't design for thickness of the bitumen, or rather the asphalt. When the method was incorporated into the NASRA, 1979, which is the predecessor of this one, Austroads document, interim guide to pavement thickness design, the characterization of traffic was converted from number of vehicles per day to number of equivalent standard axle. So previously, when we talk about traffic, we talk about the number of vehicles per day. Even now, we still talk about number of vehicles per day. For the road, we said that there are 1,000 vehicles per day or 5,000 vehicles per day. But just that, the vehicles, they are different sizes. Some are big, some are light vehicles, some are heavy vehicles. So it's not the number of vehicles doesn't really reflect the traffic, the loading. So they with the introduction of this on the NASRA and later on the Austroads, they convert the units from the number of vehicles per day to number of equivalent standard axle. So they assign different, like for a vehicle, the different how many ESA, vehicle. The small vehicle, we have smaller ESA, and the bigger one, the truck, the semi-trailer, they have a much bigger ESA. So what is the standard equivalent standard axle? So one equivalent standard axle, when they say about that, actually is equal to, this standard axle is defined as a single axle with dual tires, two tires and on both sides. So this one is dual tires, and a mass of 8.2 tons. So this one, the loading on this axle will have the total mass of 8.2 tons, and each tire or each wheel, it will divide by 4, each tire, so it will be 2.05. So each tire will get 2.05. Per wheel is 4.1 tons. This is 2 tires, but it's considered as one wheel. Is it one wheel? Yeah, one wheel, 2 tires. So there are 2 wheels. So each tire will half the wheel. Each tire will 2.05 tons. So here this says that the center to center, the tires 330 millimeter apart. Okay, rational or mechanistic procedure. So this one is the we design the material based on the pavement materials. We have to come up with the strength of the pavement materials. Previously, the empirical approach, we just talked about the strength is CBR, but here we need to like strength the material. We need to be like in the form of like MPa, the megapascal. So just like it's the same thing as the strength of concrete, strength of steel, strength of wood, the timber. So the material, so it's same category as the like structural approach. Okay, subgrade evaluation, we need to evaluate the subgrade. So even though it's we still talk about CBR, but the CBR can be converted to MPa as well, megapascal. So this one is influenced by the construction material in construction and material maintenance influence and the environment. So we select trial pavement. When you select trial pavement, you consider the traffic, because some road has bigger traffic than the others. So we have to with consideration to the traffic volume, and then we do some pavement analysis. Previously we used the hand calculation, but there's so many iterations. We need the use of the computer to do the iterations. So the computer, otherwise, we take the people too long to do the iterations by the for this mechanistic approach. So the computer will do the analysis, and then we accepted, and then if not accepted, we go back again to try a bigger one. There are some other thing, performance criteria, project reliability. Different criteria, performance criteria. You want very reliable or less reliable. We can sort of, when we analyze it, we have some sort of factor. We got a bit like the for the structure analysis, we have this the safety factor for that load, safety factor for the live load, safety factor for the wind load or the earthquake loading. So this one, it's also depend. This one, the how reliable you want it to be. So actually you can input. There are some value, some constant that can add to the design. After accepted, then we compare the designs, comparison of design, and implement design and collect feedback. So we have to accept, we compare the designs. Okay, the comparison of designs, and so this is mostly is we don't follow the chart anymore, the Africa 8.2, the empirical, the CPR methods, but we use a structural approach, and then with the help of the computer to do the analysis. So we're going to run this software as well, which we need the Circle6 or now probably even later version. So we're going to use this software to help us to do the mechanistic design approach, and then we also want to use it in one of the projects as well. Okay, this approach, this procedure address the design of the pavement in the same manner as the design of any other engineered structures. So any engineered structure like the buildings, mainly buildings. Okay, whether it's different type of buildings, steel building, concrete building, timber buildings, bridge. So we follow the similar approach to the building. In this procedure, the response of the pavement in terms of critical stress and strain under a specific loading is determined by theoretical principle using the geometry of the pavement and the characteristic of the constituent materials. So geometry of pavement, that means that, you know, mainly the width of the pavement, how wide, the thickness of the various pavement layers. So there's a geometry, the dimensional part of the pavement. Also the characteristic of the constituent materials. So the materials, they have different strength. Some of the materials, they have a lower strength, some are higher strength. So actually there's quite a number of choices that we can make for the material, you know, we can choose from, you know, depend on the requirement. The performance of the pavement, let me see, just quick this. Okay, yeah. So you see, look at the, this one is the unbound material, unbound granular material under thin bituminous surfacing. Actually this one, you know, we said that we could do with the empirical approach, but even with empirical approach, we could do use the mechanistic approach as well. So we also need to, when they do the mechanistic approach, everything, you know, the material property, we need change to the megapascal. So the vertical, the modulus, and also we have to talk about the Poisson ratio. So these are the material characteristic. So the modulus and the Poisson ratio. Okay, so I'm not going to talk too much about the underlying meaning of this thing. Okay, I think it's, you know, I think we just at the moment we just adopt it. Okay. For the cemented materials, so the top one is just the granular materials, just unbound. The bottom is a bound. Bound material, you see, look at the modulus is much higher, you know, probably like more than 10 times higher than the modulus is the cemented compared to the unbound. Okay, and then the Poisson ratio actually is lower than the unbound materials. Okay, the performance of the pavement is then predicted by the comparing the actual critical stress and strength to the allowable values. So we designed the pavement for certain period, you know, design period, let's say 10-15 years, and then there'll be, within this 15 years, there'll be some allowable values, some sort of units, and then whatever the actual one, you know, the actual strength, actual value, the traffic, based on traffic loading. The traffic loading maybe like we talk about, you know, like for example 7 times 10 to the power 6, so that means 7 million ESA. So within, let's say, a duration of 10 to 15 years, and what is the allowable value? So this if this the actual the traffic loading stress or strength that for example just now we say is ESA, if it's surpass the allowable value, the pavement will fail. If it's below the allowable value, then the rod will be considered as, you know, is the design within the limit, so it can satisfy the rod is usable within the design period. Okay. The manner in which the materials are characterized will depend on the theoretical principles which are adopted to determine critical stress and strain. Okay. For example, if a linear elastic technique is applied, then materials have to be characterized in terms of appropriate elastic parameters, usually the elastic modulus and Poisson ratio. So the material, there's different type of characteristic. We study about, I think, the Hooke's in the physics, they got something called a Hooke's law. That means elastic. When you stretch it, and then the thing will sort of it will what is it called? It will expand. We stretch it, you know, it will stretch. The material will stretch. But when you release the loading, the thing will go back to the same position. You know, that means it's the response is an elastic response. But if it's inelastic, you know, the certain thing, you know, you stretch it, and then when you release, it doesn't go back to the original position. That is called the inelastic. Here actually we use the we assume that this is elastic, so we use a linear elastic technique. That means that when the material has been stretched, and then when the force is released, it will return to the original shape, original position. Okay. Due to the complexities of the structural behavior of the pavement and of the characteristic of the pavement materials, it has only been in the past 2 decades that the mechanistic procedure has become an accepted methodology for pavement design. So usually, like I think this one, this text probably, if not mistaken, is about in the 1990s. So now probably about maybe we're more about, you know, for decades, you know, 40 years rather than like 20 years. So yeah, so actually it's still not long. Previously, prior to this, all the when they design the pavement, they all use a design chart. You know, I think even now, you know, some of the council, they still use a design charts to do for the development, the access road development. So selection of the design philosophy, you know, we look at the empirical procedure. What is the strength of the empirical procedure? Okay, so within the constraint of loading, material types, subgrade conditions, and climatic factors, the observation provide a direct validation of the pavement performance. Actually, it's quite when you have quite straightforward. You know, if you've got the loading, material types, subgrade condition, and climatic factors, the observation is quite close. Okay, but the witness, what are the witnesses of the empirical procedure? For pavement subject to different constraints such as different loading, climate, material, failure criteria, or combination of this, the application of trial observations to the prediction of pavement performance results in inaccuracies. So usually, you know, this thing, you know, the chart is been, for example, the chart just now I show you, the figure 8.4 is for the Australian condition. You know, if you apply to other places, like in the country around, like Papua New Guinea or in Indonesia or Malaysia, so the condition is different. The loading is different as well. That they got the design vehicles, it can be different. The climate is different. Certain places, like if you got more, is hotter or has more rainfall, and the material use is different as well. People use different type of aggregates. You know, some place they use the basalt, some place they use the limestone, some place they use the metamorphic rocks, and some place even, you know, is if they choose to use the local materials, for example the sandstone. Certain place, remote areas, they don't have access to any quarry materials. Some of them they use sandstone. So there'll be some inaccuracies for if you use the empirical approach, the chart methods. Factors affecting the CBR and factors affecting CBR. What are the factors affecting CBR? And the limitation of CBR methods refer to the link. So what are the factors that can affect the CBR? So there are the like soil texture, moisture, and density. These are the things that can affect the CBR. You know, what type of soil is it clay or is silt? Is it sand? It can affect the CBR. You know, the compaction is different. You know, compaction for sand, compaction for the silt, compaction for the clay, they're quite different. Moisture, is it wet? Is it dry? So you know, when the rod is wet, the ground is wet, actually the strength is lower. So the CBR is lower when the soil is wet, sock wet. Density, if you compact it very well, it's very dense compared to when it's not compacted properly. It's for example, when you fully compact, the density could be 2.2. When you not been compacted properly, the density could be about 2. So it will provide quite substantial difference in CBR. Limitation of the CBR methods of design pavement. Okay, so it has a serious disadvantage that the CBR methods of pavement design give the total thickness requirement of the pavement above the subgrade, and this thickness value would remain the same irrespective of the quality of materials used in the component layers. So we just now we look at the chart, we just look at the CBR, but regardless of the strength of material. So that means that, you know, for example, you use the pavement materials or let's say you could be using the basalt or you could be using limestone. Actually, the two things there, the quality is different. So, but they're treated as you know, if you can compact to like 20%. So 20% for the, let's say, basalt and 20% for the limestone. So they expect to provide the same result, you know, same result for the thickness, but the material, the quality of material, it does make some difference. You know, the durability, you know, the weathering. So these CBR methods doesn't consider the quality of materials. Okay, so whereas for the mechanistic approach, we consider the material properties, the strength of the properties, the modulus, and the Poisson ratios. So that one will in the mechanistic approach, we consider the quality of the materials. You know, the higher quality, you have a higher number. Whereas for this one, the empirical approach, you just any materials you can achieve like 10% CBR, you can achieve 20% CBR. So that's what it requires. So there's this limitation. The application of the empirical procedure is now limited to the design of conventional flexible pavement with thin surfacing such as spray seal or a thin layer of asphalt, for which the subgrade deformation is the dominant mode of failure. So this one, the empirical approach, only for rod with very thin surface layer, thin surfacing, spray seal or thin layer of asphalt, and the subgrade deformation is the dominant mode of failure. So we don't consider any tensile failure, so that means that we don't consider any like bound layer, only deal with the unbound layers. In order to develop a design procedure which would better direct the predict the performance of the wider range of materials and pavement configurations, the concept of pavement as a multi-layer structure was introduced. Because of the shortcoming of the empirical approach, you know, that disregard the properties of the disregard the quality of the materials. So we come up with a new approach. So as a that we consider the pavement as a multi-layer structure. In this concept, which is called the mechanistic procedure, the pavement is considered to be a load-bearing structure comprising a number of discrete layers overlaying a supporting subgrade with load applied at the surface as shown in figure. So in this mechanistic approach, we have multi-layers. You could consider usually we have this we have some like cemented material. This is bound layer. Granular material is unbound. Asphalt is a bound layer. So even we could consider a scenario like you have a thin surface surfacing, and then all the layers unbound. We could consider that as well, because the software it does provide that flexibility. So but normally for the mechanistic approach, we do allow the inclusion of the cemented materials, you know, for usually for the higher standard rods we need to have a bound layer or cemented layer, or sometimes we have the deep strand, the full depth pavement. So this one for axle with single tire, axle with dual tires. Okay. The most common version of the procedure and the one adopted in the Austroads Pavement Design guide is based on the linear elastic multi-layer theory. So the background, the principle is called, we based on the linear elastic multi-layer theory. So linear, that means that only one direction, and elastic, so we assume that the material will bounce back when the load is released. Like any analytical model, however, the mechanistic procedure requires a testing program to characterize the properties and behavior of the materials or input into the model, and the output requires verification against actual pavement. So for this approach, before we have the input into the models. When you try the pavement, you know, the there are different materials. You could try different materials, and we need to have a testing program, okay? And also you know, to establish all this the material, what are the strand of the material, you know, they can establish the what is the modulus or the Poisson ratio. Okay, we need to establish that. Also the thickness as well, and later on we need to the output part, we need to require the verification against actual pavement. Okay. Pavement design is still emerging from the empirical age and is at the distinctly different stages of development in relation to the three major influences of pavement performance: the environment, source material, and performance criteria. So these are the three major influences on pavement materials. Okay, the environment, source materials, and performance criteria. So it's still I think now we have 40 years, at least 40-50 years with the mechanistic design. So actually the software is quite popular. I think it's much more popular now. People is using the software. Okay, so Unitec we also have this software, the Cyclic 6. to do some analysis of the pavement. In fact, for the granular pavement, the all empirical design methods embodying decades of experience is still give better design solution than the mechanistic procedure. So certain there are certain design that we can still use the empirical approach. Okay, so like for example, I said the council, the Auckland Council, they still for the subdivision planning, they still use for the access rod, the type of access rod, they still use the empirical approach. In other aspect, however, the mechanistic procedure provides important advantage, just even for the granular pavement. So the mechanistic approach, they got they got a lot of advantage. So they can consider the different layers and so different the quality of the material as well. At present, for mechanistic procedure, only the primary failure models are considered in figure 8.2. The primary failure modes. There are the repeated tensile fatigue of asphalt. B. Repeated tensile fatigue of the cemented materials. And C. Repeated compressive strain and deformation of the subgrade. So there are the three types. So we have this 1, 2, 3. So 1 here, tensile strain at bottom asphalt. So this is the asphalt. So the bottom part of asphalt is here, along here. So there are some tensile strain. So and 2 here is the tensile strain at bottom of cemented material. This is a cemented material. At the bottom there will be some it can develop tensile crack. So this is a tensile strain. Strain is the expansion divided by the original length. So the strain. So you experience the cracking at the bottom of asphalt and at the bottom of cemented material. And thirdly is a compressive strain at top of subgrade. So 3 here. So there'll be some compression, the tires or the wheel just compress the ground downwards. Okay, so compressive strain at the top of the subgrade here. Okay. Okay, Table 4.2 provides a guide to the selection of appropriate design philosophy or to reflect the importance of rod. So in this table here, so certain rods, there are rod classification: local, urban rod, and rural rods, state highways and urban rods, arterial rods, freeway, motorway, and major material. So we got 2 types: is a standard and modify. Okay, so only the local rod we can use the empirical or state highway and urban rod. We could use the I think this one probably the state highway is just is a more not the motorway, not the expressway, not the multi-lanes rod, but rather is a two lane 2-way rod. They could still use the empirical approach, Okay, freeway, motorway, and major arterial rod, they have to use the mechanistic approach. Okay. So when you use the what's that, they got standard and modify the materials. If you use standard material, then you can have a choice of like here. But when you use the modified materials, then all of them you need to use the mechanistic approach. Excuse me. Empirical design procedure. Okay, so we're going to look at this is just now I think we looked through. This is the chart that we're going to use for the empirical design procedure. Okay, we consider traffic loading and also the slanting line, they are the CBR, and then this will give us the thickness of the material. The method can be extended to provide the basis for design of the thickness of each layer in a granular pavement. When designed in the particular layers, all lower layers are considered to add as subgrade with a CBR value equal to design CBR value of the layers immediately under the one being designed. This is illustrated in the design example of the selection of empirical design procedure. So this one, you see here that it says that, you know, all lower layers are considered to add as subgrade, you know, add as subgrade, which means that, you know, we only refer to the subgrade as the bottom, you know, the formation level as subgrade. But in this approach, any part of the pavement can be considered as subgrade. Okay, so when you let's say you, for this example, you know, we have, okay, we the blue line, we based on the 4.2. I think about between 2 point something percent. The blue line, I think, is 2.5%. So 2.5%. So the traffic loading is the same for all the different layers. Here is about 1 times 10 to the power 6 ESA. So, but the subgrade, the real subgrade, you know, at the bottom of the rod, the subgrade is the CPR. At the formation level, the subgrade is 2.5%. So we draw a line up to 2.5, because in between 2 and 3, 2.5, and the project the line to the left, we get about 600. So that means that the total thickness is 600 above subgrade CBR 2.5%. Okay. And the next one, we reach the green line. We reach a CBR of 10%. So, you know, the best cost subgrade 10. So the next layer, you know, we have a pit rubber. We got 10%. So that means that we are thinking of designing the sub base with 10%. So represented by the green line. So this is a 10%. So, and this based on the actually based on subgrade, the sub base is 10%. 10%. But you know, this one is CBR we just said that subgrade, you know, because here we saw generally we just refer to as the, what is that? Each layer, the lower layers are considered to add as subgrade. Okay, so the green line, so we said that the subgrade is about 10%. Even though we talk about the sub base, but we said that the subgrade. Just that is I think in this case we just say subgrade is 10%. Okay, this one is based on CBR is a subgrade, no? for subgrade. And then we go further up. It's actually 40%. You know, we got the rubber, because we're going to design for the 40%, 10%, 40%. 40% is the quarry rubber. Quarry rubber. So the red line. So actually we need to go to 40, but the top, the highest you can go is 30. So we just stop at 30 and then go left is 150 mm thick. So that means that based on the subgrade, if it can, ideally you can compact the subgrade through a percentage of like 30 or 40, you know, you only need 150 mm. You only need 150 mm thick of the pavement material. Whereas if you compact it at 2.5%, you need a total thickness of 600. If you can compact it to the this is CBR of 10%, you can have only have 280 mm thick. Okay, so these are different CBR values for the, you know, granular materials. The sub base is about 30 to 60%. The base is about greater than 80%. The subgrade, it range from like 2 to 10. So we have a look at the example here. So the typical pavement layers. So we have a pit rubble, we have a quarry west, we have a, you know, quarry rubble, we have a crushed rock. Okay, so in this example, the rod is going to carry 1.5 times 10 to the power 6 ESA, and the subgrade has strength of 2.5% using the material. I'll like follow. So the blue line is 2.5%, and then that means that we got 600 thickness of the asphalt, of the asphalt. Sorry, the thickness of the thin asphalt. This one is thin asphalt or the chip seal. So 600 above subgrade of 2.5%. We just go look at this one, this column first, and then above subgrade of 10%. That means 10% is here. This one's 10. So we need a thickness of 280. Okay, 280. If above the subgrade of 40%, is 150. 40 because the most you can go is 30. So it's 150. So what we do is that, you know, the top layers is 150. The top layer is 150, and we start from the top. You know, if you have a CBR of 40%, you know, and even though it said that the highest you can go is 30, then you only need 150 mm thick of pavement material. So the top one is 150 thick, you know, supported by the bottom part, which is 40%, which incidentally is called the sub base. Okay, so for the sub base, above 10%, above 10%. So then, so your these two layers above 10% actually is belong to the best cost. Okay, so they got two layers above 10%. So this lower base is 40%, this upper base is 90%, but the bottom, their foundation is above 10%. So above 10%. So that's why we have the top one is 150. We got to 150, and then we have because we have the total thickness, the green line show that's 280. 280 is above 10%, so we got a total of 280, and then the top one, the top layer is 150, so the remainder is actually about 130. So the above subgrade, the bottom layer, so that's here we call it, we have a definition like upper base and lower base. So the lower base actually is 280 minus 150. Okay, 280 minus 150, which give us 130. So this is the upper base, this is the lower base, and then the subgrade. This one above 2.5% is actually the above 2.5%. Actually, they are the best cost, because I think its thickness is quite substantial. We divide into two parts. Okay, so for the sub base, which is you know, the total thickness is 600 above the subgrade of 2.5%. So 600, you have to take away the 280. You know, this one So that means that the 280 is comprised of the lower base and upper base 280. So 600, the remainder will be 600 minus 280, which is what's that? Which is 320. 320. So the best cost will be 320 thick. So in this case, we because we don't have because they are all above 2.5%. What we do is that we just, if it's above like 200 thickness, we just divide into 2. So here is a 160 lower base and the upper base is 160 as well. Okay. Okay, I think we will come. I think we have tutorial as well. Then we can. I think we, after you've done the tutorial, it become more obvious to us. So this is just a theoretical part. Okay, so I think I will stop here for this part. This is the first part of the pavement design.